All right, it looks like everyone's joined. So welcome to this ATA webinar for this afternoon, looking at modeling hypersonic vehicles with computational fluid dynamics. A few housekeeping things. Everybody is muted currently. And if you've got any questions, please put them in the chat, or at the very end, we will basically unmute anybody who wants to be, so you can ask questions. So welcome again, and we'll get started. So today we're going to be basically talking about ATA engineering a little bit and STAR-CCM+. I'll be covering that. And then Chris Stojic, one of our engineers from ATA engineering, will be diving in a little more detail from both CFD and hypersonics to discuss that in more depth. So say hi, Chris. Check you're with us. Basically,
hello.
Thanks, Chris. So who are ATA Engineering? Well, basically, we're an employee-owned company of about 190 very skilled engineers, and we really have a high level of engineering skills with basically over 35 or 34 PhDs, a lot of masters, and a lot of bachelor's engineers. And we really tackle the hardest problems in the industry for engineering services. And the type of markets that we work in are predominantly aerospace and defense, but we also do some robotics and controls, some industrial mining, and more recently themed entertainment. It's surprisingly a very secure industry, but themed entertainment has become a bigger area for our business over recent years. And we are an employee-owned company, which basically means that everyone, on the line today, together with anyone who's working on a project, is an employee owner, and we really take everything very personally. All of us work together as a close-knit team, and we really strive for customer delight, and our customers certainly echo that when we speak to them about reviews and so forth. And we're also committed to excellence. We've won a lot of awards over the years. One of our most recent was the Tibbets Award from SBA. But you can see over the years, we've actually won a lot more from NASA and then NASA JPL and so forth. So our clients like to work with us. And on the services side, our focus is on analysis and test-driven design, and we're proud to help our customers meet really the toughest engineering challenges, from ground vibration tests to on state-of-the-art aircraft, all the way through to ensuring the safety of theme park rides along the way. And as part of that, being experts in Siemens software really helps us tackle those very easily. You can see some of the locations of our offices there. We're spread across the US, headquartered in San Diego. Most of those offices are in centers of aerospace industries throughout the US. And some people aren't familiar with the history, and this will be quite quickly, but basically ATA used to be a division of SDRC a long time ago, and in 2000 became its own company called ATA Engineering, Inc. And since then, we have grown across the US into those offices, and we've also grown our relationship with Siemens to the extent we're very close for basically our VAR relationship, selling and supporting Siemens, but also a very special relationship on the NX side and FEMAT, because of our history through SDRC and that relationship with Siemens. And so basically, as a platinum value-added reseller with Siemens, we do a lot of work with their software. We do support, we do software implementation, training, and we're also one of the nation's preferred training providers for many of the tools, including NX and Nastran. And so today, our key topic, though, is STAR-CCM+. And really, what we're going to be talking about is STAR-CCM+ and CFD used in hypersonic flows. And just to set the scene a little bit, ATA uses really two predominant codes for CFD here. One is LOSI Chem, which is a university code from Mississippi State, and the other is STAR-CCM+. And we'll be contrasting those a little bit. But for me, I'll be talking a little bit more about STAR-CCM+, because as you can see there in bold, it's more general CFD. It's a multi-physics solver. And really what makes it different to LOSI Chem in this context is the workflow and the level of automation that it can achieve in a production environment, really making it much more productive for design of experiments and optimization projects. So we'll see that in a minute. So just to really highlight how generic STAR-CCM+ here's a smattering of the types of applications that STAR can cope with, from aerodynamics and hypersonics through multi-phase and discrete element modeling, and even fluids and free surface flows, and even multi-phase with automotive and ice flows. It's really a complete general purpose CFD tool that happens to do lots of things very well, including hypersonics. And it's also very easy to automate. This is admittedly for a ship model, but it really highlights the point that geometry and CFD models can be wrapped into an automated loop. And if you want to optimize design and shape, there's really no better tool available to do that. This is an example of modeling resistance around a ship done with HEEDS and STAR CCM Plus, and really evaluating hundreds of different designs with no man in the loop. To really leverage the power of both CFD and your compute environment to get results much faster. So a few years ago, Chris and I did another webinar about aircraft from the 50s not being able to break the sound barrier because of geometry problems in the aircraft fuselage. And the Whitcomb area rule came about after many years of work on that. And we tried to emulate that using STAR CCM Plus and HEEDS. And so we basically created a HEEDS optimization of a supersonic fuselage, and we made the geometry parametric to look at different cross sections across the fuselage shape. And so if you look at this actual as a full design space, it's 101 times 10 to the power of 5 possible simulations. And so obviously, unattainable to do CFD and all of those. But using HEEDS with its Sherpa algorithm, cut that down to tackle 150 simulations to try and find a better design. And so in this case, again, it was automated. There was no man in the loop, and HEEDS was able to run this supersonic aircraft fuselage, and just within a matter of hours was able to reduce the drag coefficient down by 38%. And so the idea was that really all of that work that took years and years in the 50s was included in I think it took about 9 hours to do this run, and really came up with a similar answer. And so while you're thinking about this animation, which is part of some of the work that Chris has been doing more recently, imagine not just doing a single CFD model of a hypersonic vehicle and looking at those results, but also running hundreds of them to look at as an optimization or a design of experiments run to really home in on better designs. With that, I'm going to pass the ball to Chris.
Hey, yeah. Thanks, Adam. Can you see my screen?
Yep.
All right, great. Well, thanks for the introduction. With the rest of the presentation here, I'm going to start and kind of interweave within the presentation a discussion of some of the issues and challenges involved in CFD for hypersonics. And then occasionally I'll give some best practices, mainly in the context of solving hypersonic CFD problems in STAR CCM Plus, and these will be related to meshing, turbulence modeling, initialization of a solution, and accelerating that solution to convergence, and some of the physics models. And then at the very end, I'll demonstrate one of the very powerful aspects of STAR CCM Plus, which is its automation capabilities, which Adam touched on in his final few slides there. Okay, so hypersonic flows isn't, some people say, it occurs around like Mach 5 or maybe Mach 7, but it's really characterized by certain effects becoming increasingly important. I've got a list here from John Anderson's Hypersonic and High Temperature Gas Dynamics, where he first lists high temperatures becoming increasingly important in hypersonic flows, and that's certainly true, and it's probably one of the aspects that all of us are more aware of. And the implications of this can be that your vehicle is subject to much higher thermal loads, and also the flow can be affected by changes in energy storage mechanisms, chemical reactions, and ionization at high temperatures. Also, in many hypersonic flows, or many hypersonic situations that we care about, there are low density flows, sometimes making the continuum equations invalid, and you have to resort to particle methods. Or there are some cases where both continuum and particle methods can be used in different regions of that flow. There's also viscous interaction, which causes an accelerated growth of the boundary layer down the length of a vehicle, and this can affect the aerodynamic shape of the vehicle and change the way that it interacts with the flow at high speeds. There's also the emergence of this entropy layer, which creates strong wall normal entropy gradient in the boundary layer, and thin shock layers at very high hypersonic speeds. Most of the time when we're doing continuum CFD, what we're all focused on is really this item at the top, the high temperatures, and that's what I'll be touching on a little bit in this talk. So just briefly, I want to talk to you about some of the things that ATA engineering does in hypersonics. Here I'm showing just a few of the examples related to aerothermal modeling, hypersonic panel, fluid thermal structural interaction. On the top right, we've got a neat animation of the ablation of a nozzle throat. On the lower right, we do a lot of work in advanced composites modeling to provide accurate models for the advanced materials that are needed for hypersonic flight. And then in the middle, I'm showing a video of a wind tunnel transient air load prediction tool, which we call TAPT, which enables us to provide predictions of kind of these violent transient air loads that are experienced in high-speed wind tunnels when you want to actually test these components. So as Adam mentioned, at ATA we use primarily two CFD packages, LOSI-Chem and StarCCM+. And we use them, they are both very capable tools, and we use them in different situations. So one aspect of LOSI-Chem that's very attractive to us is that we can modify the source code and add modules so that we can really use it to tackle the very hard and kind of esoteric problems that we're interested in. And we've actually been developers of LOSI-Chem for a long time, working with Professor Luke. And then StarCCM+, which, as you can tell from the introduction, we'll focus mostly on today. It's a multi-physics commercial package, and it's really emphasizes efficient workflow, automation, and high fidelity with a large range of physics models. And both of them, as I mentioned, produce accurate results. This is just a simulation of a Mach 10 kind of entry capsule here. And I ran them in both codes, and both produced similar results. The numerics were slightly different in both of them, so you can tell that there are some features that are different, but the shock standoff is essentially at the same location. And again, at ATA, we decide which code we want to use depending on certain aspects of the problems we want to tackle. So I'll start by getting into some best practices related to meshing. So as I've mentioned previously, surface heating is a large concern in the design of vehicles for use in the hypersonic environment, and that's why we use these prism layers and solid boundaries so that we can generate these generate very high resolution in the wall normal direction to capture the large flow and thermal gradients there. If anybody is aware of this phenomenon called the carbuncle phenomenon, you can also use prism layers at the front of, say, a bluff body or a blunt body to kind of align the mesh with the shock there by creating prism layers that are thick enough to envelope the shock, and that can help kind of ameliorate the carbuncle phenomenon. We also at ATA recommend a wall Y+ value of less than 1 to really capture the very high thermal gradients that you see at the surface of the vehicle in hypersonic flows. Also, as we're all aware, in any flows that are higher than the speed of sound, you see shock waves, and the position of these shock waves isn't known before you run the solution. You can get estimates from analytical solutions and such, but really the position is based on the solution to that particular problem. And so you've got these shocks with these large jumps in flow quantities, and you need a mesh that is locally refined in order to capture these shocks. And this is where adaptive mesh refinement, or AMR, comes into play, because it adaptively changes the mesh to place cells in regions of high gradients. So a little bit more about how that is implemented in StarCCM+. AMR, in this case, will respond to a user-defined metric to identify unresolved gradients. An effective user-defined function for this will kind of quantify the flow, the gradient of the flow across one cell. So I've got it written out here. It's like you take the gradient of some flow variable f and multiply it by a cell size, and then you can say, okay, now how much do we want to limit the amount that flow variable changes across one cell? Kind of sorry for the busy slide here, but I've kind of got that shown in this XY plot here, where on the original mesh, say we've just got one cell from x equals 1 to x equals 2, and the flow changes by 2. So if we were to cluster, say using AMR, some points along that or around that region, you can resolve much higher gradients in the solution than you would on the original grid. And this has implications for the shock strength and really the entropy generation downstream of the shock. So speaking in StarCCM+ language, one example AMR function that I use is the magnitude of the gradient of the Mach number multiplied by what's called the adaptation cell size, but it's really the existing cell before the AMR operation. So I'm kind of showing what this looks like on the right there. The original grid, or what I'm calling the coarse grid, is at the top there, and I'm showing my AMR function where I've told it, okay, in areas where this quantity G, or the change in the Mach number, is greater than 0.8, we want to subdivide the cell to a specified limit so that the mesh doesn't blow up. In regions where the change is between 0.8 and 0.2, we just want to leave that cell alone. And then regions where the change is less than 0.2, we want to coarsen that back towards the original grid. So as you can see, we've got these large red regions around where this bow shock is. And then as AMR goes, the AMR operation continues, you can see that it clusters points along the bow shock and in the wake in places where these high gradients are detected. So that's done adaptively and automatically without the user having to direct the mesher to throw more points in that spot. Now moving on to turbulence. Turbulence in any situation is very complicated. In hypersonic flows, it becomes more so. A lot of the times when we're working on problems in non-hypersonic flows and maybe a canonical kind of shape, we can go back to our textbooks and say, okay, for flow over a cylinder, we have this critical Reynolds number at which the boundary layer transitions from laminar, as I'm showing up in the upper left, to turbulent, or in the upper right, sorry. For example, in an incompressible plate, incompressible flat plate, this transition Reynolds number occurs around 5 times 10 to the 5th. However, it's not that simple in hypersonics. The transition Reynolds number, as I'm showing in this kind of equation here, is a complicated function of multiple parameters. There are 18 in this equation. So the transition location is very problem specific, and as I'll show in the next slide, it's oftentimes inconsistent with observations and kind of our experience at lower speeds. So here are some of those observations, kind of non-intuitively, the transition Reynolds number can change with Mach number and actually become delayed at high Mach numbers. In this plot on the right here, which is for a specific geometry, you can see that around Mach 4, at least for the solid line, the transition Reynolds number starts to become delayed pretty rapidly, moving downstream on the vehicle. One other kind of interesting thing that this plot shows is that the transition Reynolds number also increases with unit Reynolds numbers, so that, meaning in higher density flows or higher velocity flows, Reynolds number may increase, or the transition Reynolds number may increase. Also shown in the figure in the middle here, there are strong three-dimensional effects. In this case, this cone is increasing in angle of attack, and the transition on the windward side is being pushed aftwards as the angle of attack increases, whereas it's being pushed, forward on the leeward side. If you are working with a vehicle with a blunt nose tip, that may delay transition. However, if the nose tip is too blunt, it may hasten transition. So that's confusing. Also, the same for a cold wall. A cold wall has been shown to delay transition, but if it's too cold, then it may advance transition. So all of this is just to say that in a lot of these cases, in hypersonic flows, the transition Reynolds number is delayed past what it would be expected. And so turbulent boundary layer is actually not always present in hypersonic simulations. However, if we are using a turbulence Reynolds number, there are some recommended settings, at least for star CCM plus. The recommended model is the K Omega SST model with the A1 coefficient set to 0.355. This, as shown on the right from a NASA report, was shown to better predict kind of the separation location and extent of that separation bubble. Also, it's recommended that you use a quadratic constitutive relation, or QCR, which better accounts for anisotropy and secondary flows. And then it's for these specific simulations, it's best to specify K and omega explicitly in the initial conditions, boundary conditions, in various regions from what their default values are. So the recommendation is K, or turbulent kinetic energy is 1 times 10 to the minus 6 times the velocity squared, and dissipation is, or dissipation rate is 5 times velocity over some characteristic length for the problem. So these values, for instance, for a Mach 10 flow at 70,000 feet over a 1 meter vehicle would be 9 and 1.5 times 10 to the 4 respectively, and these are very different from default values. So moving on to solver settings to mitigate inaccuracies and the carbuncle phenomena. I mentioned briefly the carbuncle phenomenon on a previous slide. What that is in some cases, mesh misalignment with the flow solution can produce spurious vorticity and shockwave deformations, which kind of propagate downstream and create oftentimes uneven wall heat flux on your vehicle. And so these are numerical and not physical, and you want to get rid of them. So the developers at Star CCM Plus have made modifications to their AUSM flux vector splitting scheme to kind of help out with that issue and correct for the mesh misalignments that lead to the carbuncle phenomena. It's also recommended that you use the MUS CL third order differencing scheme, and it's recommended that the default AMG solver tolerance is 0.1. It's recommended to reduce that to 0.001 to really ensure that you're converging at each iteration and avoid error stack up. This will impact runtime, so you have to kind of weigh what you're more interested in for that particular problem. It's also recommended that you use ILU under relaxation instead of a constant value. Also in these hypersonic cases, as we've kind of hammered on, they're difficult. And one good way to get a usable solution and get it quickly is to start with a good initial guess at what the solution is. If there's a solution will oftentimes diverge if we just start off by plunging our vehicle into a bath of hypersonic flow. So starting with a good initial condition is a good idea. And in Star CCM Plus, there's a grid sequencing initialization setting that helps out with that. So what it does is it uses a multi-grid technique to solve for a good initial condition. I kind of illustrate this on the right. This isn't exactly what happens. This is just my kind of manually generated grid kind of illustration of what's happening. But a series of coarse meshes are generated off of the kind of I guess the fine mesh that you create that you want to solve your solution on. An approximate solution is computed on the coarsest grid, and after either a number of maximum iterations or until that's reached after it's reached some convergence, that's then interpolated onto the next finest grid, and so on until you reach that finer that initial fine grid that you generated, and hopefully have at that point a good initial condition for your simulation. Another great aspect of StarCCM Plus that helps you accelerate convergence is this automatic CFL setting. So what it does is it aggressively adjusts the CFL number in response to how much the linear algebraic solver is struggling to solve the system at each iteration. So you can see kind of in this plot on the bottom here, I ran 150 iterations and kind of watched the CFL number change under the direction of the auto CFL setting. And you can see that my CFL number, I started at 0.1, and it continues to grow up until 5.5. And then there's a change in the AMG solver, which indicates that, okay, it's having a little bit tougher time solving the problem with that CFL number. So the auto CFL kind of adjusts so that less time is wasted in the AMG. And this dance kind of goes back and forth and really gain the most efficiency and converge this solution as quickly as possible. Now, I'll just briefly speak about the physics models for high temperature hypersonic flows. Again, at high temperatures, the effects of various internal energy storage mechanisms, dissociation and ionization become significant. Around 800 Kelvin, the vibrational energy storage mechanism becomes excited so that the specific heats can no longer be assumed constant, and they're more accurately described as functions of temperature. Above 2000 Kelvin, oxygen starts to dissociate, and then 4000 Kelvin is when nitrogen begins to associate or dissociate. And then above 9000, you start to ionize the air. For these simulations in air, StarCCM recommended model is the equilibrium air model. So it's important to note that this doesn't explicitly solve for dissociation and ionization, but instead uses curve fits that account for chemical reactions and ionization, and modify the energy, the specific heat capacities and transport variables as functions of temperature and pressure. StarCCM can do reaction chemistry and has a large number of models to do that. It's expensive to add those models in, and reaction chemistry might not be important unless in a non-equilibrium flow, or unless species is needed, the species concentrations are needed for interaction with surface reaction, for instance, in ablation. However, if you're modeling ablation, just getting the flow right isn't enough. You need detailed information about the surface composition and how it ablates, and that is an effort in itself. So in these cases at ATA, we would use our tools where we've coupled loci chem with our fluid structure material interaction capabilities that include advanced material models and ablation response models. But one great thing that I love about StarCCM Plus is it really saves me a lot of heartache and time, and that's because it's very good for automation. all of these things that I show here, CAD, mesh, solution, analysis, and post-processing, they're all included in a single environment. You don't have to jump back and forth between different packages. For CAD, it's got a native CAD tool within it, or it links up nicely with more dedicated CAD tools like NX. It's got robust and intelligent meshing algorithms, which generate very high quality meshes without much much direction from the user. It's got a comprehensive, high fidelity suite of physics models that allow you to solve whatever problem you'd like to, as Adam had alluded to with this slide, on all the different physics models. And then got powerful and robust solvers to converge on the solution as quickly as possible, and post-processing tools. So in this case of this reentry vehicle, just one example that I want to show. I ran this, over a portion of last weekend on my desktop computer, and really just set the problem up and hit go, and STAR was able to make whatever geometry modifications are necessary, mesh it, use AMR to produce the highest quality mesh as the solution evolved, so that we have this this mesh which really resolves this bow shock. And then when it detected convergence, it went and saved my solution. So just in review, in this talk, we've kind of reviewed some of the issues and challenges in hypersonic modeling, and I've given you the recommended best practices for attacking these problems in StarCCM+, and then given you a taste on how StarCCM+ can save all of our time, so that we can spend time doing our engineering work and let the computer take care of all the tedious kind of workflow tasks. So that is the end of my talk. I can pass it back to you, Adam.
Excellent.
Or I can take any questions.
Well, Chris, that was fantastic. Thank you so much. I wanted to remind everyone that the whole presentation is recorded. So if you want to come back to it and pull out some of those recommendations for best practices, it's easy to do on ATA's website and our YouTube page. So I think I'm going to ask Jonathan, who's been collecting questions, to go through those now. Over to you, Jonathan.
Perfect. Thank you, Chris. Thank you, Adam. We do have a couple questions, so I'll read those in. And while we're going through those, please feel free to keep submitting questions in the chat or in the Q&A tab. You can also message me or any of the panelists if you want to be unmuted. But with that, we'll go ahead and kick off the questions. So I think kind of starting with AMR, is that process parallelized?
That's for you, Chris.
Yeah, sorry, I had my mute on. The AMR process is parallelized. It's I want to say 1.5 years ago, AMR was it was improved so that it runs now very quickly, even on parallel problems, and just works on subdividing cells where needed.
Okay, awesome. I think one or two other questions on AMR. First, I guess, can or should you do AMR in the boundary layer mesh?
Yeah, it's so if you look at the StarCCM+ docs, it's kind of discouraged. So by default, AMR is disabled in the boundary layer. You're given the opportunity to enable it, but you just have to really understand that it's going to more significantly affect your cell count and your mesh size more than just running AMR outside of the boundary layer. But you can enable it, and it is recommended sometimes, especially if you have immersed the shock within the boundary layer and you want to further refine within the boundary layer to more accurately capture that shock.
Okay, perfect. And then how small can the cells go in AMR? Like, what keeps it from just going on forever?
You can set the first thing is you can set the number of levels. I mentioned that AMR works by subdividing cells. So if we've got, say, a 1 inch by 1 inch cell, and that's marked for refinement, that's going to become 4, half-inch square cells. You can set the number of levels of refinement that you want. So I think by default, the number is 2. So that 1 inch by 1 inch cell, the most it'll ever generate is 16 1/4-inch squared cells. But if you're thinking that, hey, I think I'm going to have to resolve smaller features than this, and I don't care about the mesh kind of getting a little bit bigger, you can change that number to whatever you'd like, and AMR will continue subdividing that cell.
Okay, cool. Couple other questions, and I encourage questions to keep coming in if you have them. Kind of switching gears off of AMR. You were mentioning complexity in transition Reynolds. How does STAR determine the turbulence models?
So STAR offers a pretty wide variety of turbulence modeling options for you to choose from. It doesn't have, like an accurate transition prediction scheme, but it does allow you to kind of delay transition until a point that you think is realistic for transition to start. But it's really, it's kind of based on user input.
Okay. And then Adam, this might be the final question, or Chris, I guess is for you, but just a heads up. You had mentioned kind of at the beginning and middle that we use LoCiChem in some areas. Are there any ways that STAR comes into that workflow as well? Like, would we ever use STAR like for meshing or anything like that, or are they just totally separate?
Yeah, I in fact, LoCiChem, you can use a number of meshing tools for it, STAR being one of them, and I really prefer using STAR to generate my meshes because it's very easy. It saves me a lot of time, and as I mentioned, it generates high quality meshes, and the mesher is based on numerics, but also on the developer's experience, meshing for CFD and based on best practices for meshing geometries for CFD simulations.
Okay, cool. Yeah. And one other thing I'll throw in there that I think has been interesting is we've even seen the STAR CCM+ mesher start to be adopted by other Siemens software tools. So like FEMAP has recently brought in a few new meshing techniques that are based on the STAR mesher. So good stuff there. I have a couple other questions that just came in. I think you've already caught or covered them. One asking if AMR, I guess, Chris, if you use AMR within the boundary layer, I think you sort of touched on that. And you also sort of touched on the ability to use STAR generated meshes in those KIM CFD solves. So I think with that, Adam, I'll turn it back over to you. I think we're good.
Excellent. Thank you, Jonathan. Thank you, Chris. And thank you, everyone, for joining us this afternoon. Hope you enjoyed it. And join us, in incoming webinars from ATA. Thanks a lot, everybody. Bye-bye.
Thank you.